This video is about finding all the sets making up a row of Kakuro. Kakuro is a popular puzzle found in newspaper these days. Here is a puzzle. In this puzzle we can see that this line requires 4 numbers from 1 to 9 and that their sum must add up to 27. What we're trying to do here is to find all the sets that can make up this 27 using only the numbers 1 to 9, and here we're using 4 of them. There are many ways to find those sets, and the method demonstrated here is not the fastest one, but it's a pretty good one. So let's start by looking into finding sets of pairs adding up to a specific sum. Let's say we want to find all the pairs adding up to 14. In general, the first number can be 1 to 9, and the second number can only be the sum that we want minus that number. So for example, there are 8, 9, it's hard to see how many pairs there are here. Let's make sure we can see the enclosures. We're going to use the user command box and turn it on so that we can see the enclosures. And try again. Now that's better. These are all the pairs adding up to 14. Some are duplicate. For example, these here are duplicates. And some are invalid. Number 13 is not a valid number in a pair. And a couple of 7s there that should not be there. You can't repeat the numbers. If we keep the sets in increasing order, we can get rid of all the duplicates. And to do so, we can restrict the first number to be in the range 1 to 6. We know that because there's no need to start with a 7 or more. A 7 would have to be followed by an 8, and 7 plus 8 is already exceeding 14. So given the sum that we want, we can always find the largest combination to be a certain number followed by that number plus 1. Or, as we can see here, that number plus the number that follows it, in our case, equals 14. So the maximum that n can be is 6.5. But since we're dealing only with integers, so 6 is the maximum we need to use here. Here's the function pairs that should find all the possible pairs for a given sum. As you can see here, we're taking the sum we want, subtract 1, divide by 2, find the maximum that we need, and generate all the numbers up to that number. Then we take the difference between our sum and all those numbers, and we record only those that are in the range 1 to 9. Finally, what we do is that we concatenate the initial numbers and their difference, and we only keep the ones that we need to. So let's try it with 14. Yep, seems to be working fine. Let's try it with 10. Yep. How about triples? Well, triples is going to be the same thing. The largest sequence will be a certain number n, followed by n plus 1, followed by n plus 2. These 3 numbers must add up to the sum we want. In other words, that n must be the sum that we want minus 3, divided by 3, and floored because we only deal with integers. Let's try again with our sum of 14. Here's the number we need to stop at, number 3, so we only need to try with 1, 2, and 3. Now let's try 1 followed by all the pairs of 14 minus 1, 13. So we have 1, and all the pairs that add up to 13 should give us all the triples that add up to 14. Same thing with 2. It's going to be a 2 followed by all the pairs that add up to 14 minus 2, 12. And same logic applies to 3. 3 is going to be concatenated to all the pairs that add up to 14 minus 3, 11. Except that there's a problem here. We should ignore any pair starting with a number smaller or equal than our first number. The first one has already been done in the sequence starting with 2, and the second one is illegal because it got 2 3's in there. So we will modify pairs to accept an optional left argument specifying those to ignore. So as we can see here, we set the left argument to 0 if it's not set, and then we use it to drop any number that we don't want. So let's try with pairs of 9s, and if we decide that we don't want the one starting with 1, it works. So now if we try again with our triples adding up to 11, now it works. And of course the 2 other ones also work. Now if we do it all together, we can take all the numbers 1, 2, 3, each one concatenated to each one of the pairs generated by dropping 1, 2, or 3 from the sum of 14 minus 1, 14 minus 2, 14 minus 3. Oh, we didn't do it right. We forgot an extra each. Now that's better. There's still a business of as many enclosures there. We need to glue them together. Here's function triples, which finds the starting range and then does the business of concatenating just like we did before, and then putting the numbers together and finally disclosing the final result. And that works. Okay, so this business of doing this each thing is getting out of hand. Maybe what we should do is change the data structure and use matrices instead. Let's rewrite our functions. Here's pairs in matrix form, so pairs M, and as you can see, the difference here is that, well, let's compare them. You can see here that previously we were concatenating the numbers together. Now what we're doing is we're putting them into matrix form. It's very little difference. So let's try it with 9, and yep, it still works, but the format is different. And if we want the enclosure form, we can always use this, or for those of you who have access to V14, we can use the rank operator, which encloses rank 1, that is all the vectors, our result. Now let's see triples if the matrix format is this one, and just to compare them, it's exactly the same technique, except that we have fewer enclosures now, one fewer enclosure. The overall result is going to be a little bit cleaner. This is what we had before. Okay, what about quadruples? Well, it's very similar. The largest possible set will be n followed by n plus 1, followed by n plus 2, followed by n plus 3, and where we're going to be stopping at will be the sum minus 6 divided by 4. There's a pattern here. It looks like the number to subtract from the sum to determine the limit is the sum of iota n minus 1, n being the number of digits that we have. So quadruples should be like this. Here we have the sum minus the sum of the first 3 numbers, 4 minus 1, divided by 4, floored, and this gives us the initial number. And then we concatenate that number on each one of the triples given by our sum minus this number, just like we did before for triples. So if we try with 27, oh, there's something wrong here. We have 2 5s, one after the other. That's because we forgot to specify a left argument, just like we did with pairs. So let's put it in and try it again. Now it's working. Okay, let's have a look at n tuples. This is a general function that will accept a sum as a right argument, just like the other functions, but it will receive the number of digits that you want on the left. So for example, 4n tuples 12 gives us 2 answers. This is a recursive function. Let's see how it works. On this line we set the number of numbers we want, and the skipping number, the same number we gave as left argument to the functions pairs and triples, the number we want to skip to. On this line, we check the case n equals 1. This is the simplest case. If we only want one number, then the sum must be the answer, and we return a 1 by 1 matrix, unless it is greater than 9, in which case we return a 0 by 1. On this line, we find the largest digit to start with. On this line, we check that the digit is not to be skipped, and if it is, we return a 0 by n matrix. On this line we generate all the first digits to start with, and on this line we do the actual work. We concatenate each starting number to each result of the same function, which has been called with one number less than we call this one. So if we called it with number 4, we're going to call ourselves again with the number 3, to which we concatenate our starting number, which will become the skipping number inside the call. And to the right we give it the sum minus the starting number. Finally, we put all the matrices together and disclose the result, because insert always returns an enclosed result. And the ultimate test is to find a 9-digit row consisting of the numbers 1 to 9, all of them. They cannot repeat, so that's the maximum number we can have. And of course they're going to have to add up to 45. There should be only one answer. And there is one. It's pretty fast too. So let's have a look at how long it takes to run this function. It's too fast. We have to run it at least for 1 second. So we'll say repeat equals 1 second. And that will give us, so that's not too bad. How much space does it take? Yeah, pretty good. Alright, I hope you've enjoyed this. Please leave a comment if you feel so inclined to. Goodbye.